couple of small stories like hydrogenation. Hydrogenation is a small story for which there is no mechanism is necessary. Hydrogenation is adding hydrogen gas, hydrogen gas, that means H2G. Whenever there is a H2G is a reactant, we call it a hydrogenation. This can be also called reduction. This can be also called reduction, but not all reductions are hydrogenations. Remember that. Hydrogenation is reduction, but not all reductions are hydrogenations. And you will see the twist of that in a little later. Okay? Hydrogenation. What is the definition? Let's go for what oxidation reduction means. By definition, oxidation is first definition. First definition was add O, reduction is remove O. Adding oxygen, removing oxygen. That was the first definition. That's why it's called oxidation. Oxygen was part of the game. But then scientists started seeing that not all oxidations had oxygen involved. So they said removing hydrogen could be considered oxidation. Adding hydrogen is considered reduction. So if you look at Mendeleev's periodic table, Mendeleev's periodic table is based on adding oxygen and removing hydrogen as the game. Because if you look at the headings, there were 8 headings. First one was R2O. Second heading is RO. Right? This is group 1, group 2. Right? And if you look at halogens, they were called RH, RH2, RH3. If you look at this is group 5, group 6, and group 7. Right? Group 5 is labeled as RH3. Group 6 is RH2. Group 7 is RH. So most common elements available at that time were oxygen and hydrogen. So definition of reactions were based on reactions with oxygen and hydrogen. Right? Group 4, group 3, actually wherever it is, Mendeleev didn't have transition metals. So group 3 was labeled as R2O3. And group 4 was labeled RO2 or RH4. And that became RH3, RH2, RH. So this is an interesting way Mendeleev created the periodic table. There's a basis of Mendeleev's periodic table has to do with oxygens and hydrogens. That's just a historic issue. Let's leave it at that. What is the new definition? Most universal definition now is removing electrons, add electrons. So if you add electrons, reduction, removing electron, oxidation. You might have seen that Leo says Gur. Leo says Gur. Losing electron oxidation, gaining electron reduction. Right? That's just a mnemonic. So I just want you to be aware when we use the word reduction, reduction could be adding hydrogens or adding electrons or removing oxygen. Right? So in this case, addition of hydrogen is fitting this description. But when you use H2 as a reactant, we call it hydrogenation. So it's also called catalytic reduction. Now, interesting thing about catalytic reduction is hydrogenation is usually when you use precious metals. What is precious metal mean to us? Precious. There are lots of metals. Precious metals are something that do not get destroyed very easily. They don't get oxidized. Aluminum gets oxidized or iron gets oxidized, so it's not precious, right? Platinum is precious. Gold is platinum. Gold is precious. Ruthenium, rhodium. These are precious metals. Okay, these are expensive metals because they do not get destroyed. Some of them are used as part of the currency, right? Silver is used part of the currency. Gold is part of the currency. Why? If the coin gets destroyed, the value is going to be gone. So jewelry is not made by iron or aluminum. It is made with gold or platinum because these are precious metals. Now, when we talk about catalytic process, these metals are used for a support system. But you don't need much of this. You just need a tiny bit of powder. But greater surface area is created by charcoal. Charcoal or carbon black. Okay, carbon. That's why we say reaction is written like this. H2G on PTC, platinized charcoal. This is called activated charcoal. Activated charcoal is used for lots of different purposes, such as cleaning water, right? Filtering water. Under the counter water filters, they use Brita filters. They contain activated charcoal. Your refrigerator, when you are using filtered water there, they use charcoal canisters. In any case, now one thing that we have to be cautious about is this reaction is a gas. A gas doesn't like to be participating in a reaction, so we got to trap it. So charcoal is a good trap. Charcoal is known to have cavities, fibers. So in those cavities, hydrogen is trapped as a active participant. But how do you bring them closer? We always use some solvent. Ethanol is a good solvent. Not only that, what would happen to hydrogen gas as you raise the temperature? It's going to escape. If you raise the temperature, hydrogen can escape. So usually this reaction is carried out at a lower temperature, right? So these are the conditions for the reaction. So every one of them have specific value here. Temperature, solvent, a cavity, an activated metal. This is the reactant. If anything is missing, this hydrogen and this one are not going to get together. They don't have a chance of reacting. So every one of these catalytic hydrogenations, catalytic reductions or catalytic hydrogenations will require something like this. They do require lower temperature. They do require a solvent that will bring them together. They do require a charcoal, which is, or something equivalent. Sometimes they use barium carbonate or barium sulfate. What is the other one? Calcium carbonate is also used as a cavity, a trap. It's a trap for hydrogen. So what do we get? Interestingly, the product is not fancy. We added hydrogen. That's it. We just added hydrogen across a double bond. That's why it's called hydrogenation. Now, one thing that is unique about this is this addition is syn. Syn addition. Do we have regio selection here? Do you have a regiochemistry here? Do we have regiochemistry here? No, because if you look at the product, each of them got hydrogen. Which came when? Which one was chosen when? So there is no regiochemistry. There is no regiochemistry here. That means there was no regio selection. But there is definitely stereo. Is it selection? Again, we don't know the mechanism, so this is called stereo-specific. Not stereo-selective product, it's a stereo-specific product. Okay? There are some theories that there are some people who have used a cartoon to explain how that happens. Right? Now this is probably not a best model. So let's say we have a catalytic surface, metal surface, right? Metal surface, what is metal known for? Metal is known for electron flow. They are good conductor of electricity, good conductor of thermal conductivity, right? So essentially what this alkene does is it sits kind of rests. It's like a park bench. So it kind of rests its electron on this. And hydrogen also does the same thing. And as they start interacting with the surface, they start separating. The pi electrons start separating. This is just a story. And what happens is one of the hydrogen attaches to one of these carbons, and when it does that, this is the next movie. You're talking about a cartoon I'm drawing. This is my version of the story. You don't have to approve of it. At this point, I have one hydrogen that was there, second hydrogen that was there. This third hydrogen is the one that came from here. Okay. Now, after one hydrogen is added, the second hydrogen is still sitting here. Okay. When they separate, this carbon and this carbon, this hydrogen interact, and that's how they make that bond. How they did it, I have no idea. This is something that we have to inquire organic gods. Okay. If you are not religious, you got to take up a religion now. So then what happens is you have next hydrogen attacks here. And this is a cartoon that I can simply draw, and nobody is going to be there to argue with me saying that that's not how it happens. And nobody is going to say, yep, exactly how it happens, I know it. So there is no proof to this. But only proof I have is what? Only proof I have is these two hydrogens happen to add on same side. These two hydrogens happen to add syn to each other. That's all we know, right? At that point, this surface is no longer needed. The surface is no longer needed. That means catalytic surfactant. Is it get used? No. Surface is still there. The park bench is still there. Next couple can come and sit in. So this kind continues. So this molecule floats away. So the reaction between alkene and hydrogen happens this way. This is my imagination. That doesn't mean that has to be the way it should be. And this continues. Cycle continues. Next molecule comes in. That's why catalytic surface, as I use the word park bench as an analogy, because nobody takes the park bench with them home unless it is loose and you want one at home, right? Generally, benches in a park stay where they are, but people go sit and get up and walk away. People go sit, get up and walk away. Does it matter who comes and sits? No. So these two molecules came and sat, they got married, they walked away. Done. Next pair of molecules come and sit in, they get married, walk away. That's what is my imagination of catalytic process. Alright, this is hydrogenation. Our next story is hydroxylation. Since mechanisms are not known, we can only leave it up to our imagination. What is appropriate is left to our imagination. We can only imagine what could be happening, right? Hydroxylation means adding OH and OH. So we are adding two OHs across a double bond. So overall reaction is this. You have a OH. Oh, what am I doing? What am I doing? What am I doing? I gotta have starting molecule. Is this? This is alkene. When it is treated with whatever reagent we are going to use, is going to give you a OH group here and OH group here. And interestingly, what term can I use? It is a stereospecific product. And we don't know how it happens, and there is no carbocation formation, that there is no choice, so there is no regiochemistry or selectivity. Just like here, no regiochemistry or selectivity. Okay, so there are two sets of reagents that we know how to do this. One is we can use potassium permanganate. Now potassium permanganate is simply potassium cation and permanganate, MnO4 minus, right? That's the actual player. Potassium permanganate under mild conditions, remember we have to under cold condition, cold aqueous condition, okay? Under cold aqueous condition we get this. And having this sin is what tells a little bit curious thing. How does this happen? Well, people are theorizing that these oxygens are coming from manganese is a strong oxidizing agent, right? So there are some pictures that are drawn to show permanganate looks like this. It's a 7+ oxidation state. It has 7 electrons. It has Mn is 7. It's a 7+, right? So what happens is we think that simultaneously this carbon and this oxygen, this carbon and this oxygen are interacting with each other. That's just the story. That's just the narrative. And that is why both of them are on same side. They did not go flip. One didn't go there, one didn't go there. They are on same side because these two are going to be interacting. That's the only thing we know. Anything more that you see in any pictures, any literature, any book is unsubstantiated because there is no evidence to any of these mechanisms. So this is where I would like to end. There is nothing more there. Permanganate does that. Only thing that you have to keep in mind, it's cold because hot condition gives you totally different product. Be careful, this is a catch. This cold condition. Now how do we define cold? How do we define cold? If I don't want to write cold, I can write mild. Or what is the room temperature? Room temperature is 25 degrees Celsius, right? Consider that as reference. If the temperature is, if somebody writes here 10 degrees Celsius, what am I saying? Aha, we are talking about cooler condition. If I wrote 90 degrees Celsius, means what? It's hot. Do I have to write hot and cold? Do I have to write mild and strong? We don't have to write that. I can simply write 10 degree, which is less than 25, so it's a cooler condition. 90 degree, more than 25, hotter condition. Could I have written 60 degrees instead of 90? Yeah, right? If I had written 70 degree, it says the same thing. If I said, could I say it is going to be 120 degrees? Is it possible for me to write 120 in this case? Intelligent answer, please. Could I be writing 120? You would say 120 is larger than 25, so it's okay, it's a hot one. Don't think linearly. Who are we talking here? Water. Can water go above 100 at any time in terms of liquid condition? No. So you cannot write temperature more than 100 for this reaction. Unless you are talking about gaseous, right? Unless you're talking about gaseous, or if I say minus 25 degrees Celsius, oh, that's cold, all right. Minus 25, H2O is in solid form. You won't be able to make a solution. See, this is a solution. To be able to make a solution, this has to be in liquid form. See, there are small glitches that you may want to be aware of, okay? So, if you are told it's cold or a mild or a 10 degrees, they are same thing. If it is hot, strong, or any temperature above 25 but below 100, It cannot be over 100. Keep an eye on that. The other reaction that accomplishes the same thing is osmium tetroxide. Now osmium tetroxide, osmium is a metal, followed by sodium bisulfite. Okay, it gives you the same product, the syn diol. Whoa, I named it, didn't I? This is called syn diol. Why is it diol? Diol means there are two ols in it, and they are also vicinal diols. Vicinal means they are on adjacent carbons. Vicinal diols. Okay? There is nothing more to hydroxylation than that. This is where the hydroxylation story ends. Okay? Hydrogenation, hydroxylation stories end. I'm going to pause this video right here.